afternoon. Thank you so much for joining in for today's webinar. My name is Meg, and I work as a solution architect and engineering manager at NVIDIA. Majorly, myself and my team focuses on a lot of applied deep learning research projects, and we work very closely with multiple different customers, ranging from government to enterprises, in terms of building and deploying large-scale deep learning platforms for the country. So let me, quickly get started for today's session, which would majorly is going to focus on, how do you build large-scale inferencing platforms using Triton Inference Server. Now, again, for those of you who are already have been working in this field for quite some time, you must have realized that, building models is one part of the entire story, but how do you really and effectively deploy these models at scale is another very important problem. And the reason why it's important is because the cost of serving these deep learning models at scale uh, are extremely expensive. And in order to do that very efficiently, wherein you are saving enough money for the company by building this efficient platform, is eventually going to make the cost of using that particular service more cheaper, and in return is going to reduce your overall uh, you know something, a term we call as TCO, which is total cost of ownership of that particular uh, feature within your application. So with that, before I move forward and talk more about Triton, what I really want to do is I want to quickly give a quick idea about where you can see this entire uh, space of generative AI and deep learning is moving towards, and why just deploying a single model is not the only thing that would be required in the future. So here, before I get started on Triton, I just want to show you some of our applied application projects that customers are using uh, in the world, and how there is a combination of computer vision, natural language processing, speech recognition, speech synthesis. How does all of those technologies come together and build these end-to-end solutions? And another part which is important is that all of this, one of the backend inferencing engine is being used using Triton. So let me quickly show you an example of a talking kiosk, which essentially enables the entire life cycle of ordering food products in a particular store.
Hi, welcome to Shannon's Cafe. How can I help you?
Can I have a cheeseburger with a side of onion rings, please?
Would you be interested in our popular toppings for cheeseburger like bacon and fried onions?
Yeah, let's do it.
Done. Added cheeseburger with bacon and fried onions. What else?
What protein options do you have?
We have multiple options. I recommend the double protein burger. Would you like that?
Do you have any vegetarian options?
I can get you a black bean patty instead. Would you like that?
Sure.
Okay. I have added double protein burger with black bean patty to your cart. What else?
Do you have any sides?
We have these 3 vegetarian items: French fries, onion rings, and fried pickles. What do you like?
I'll have the French fries instead of the onion rings, please.
Sure. Would you like some garlic on it?
Yes, please.
Okay. I have added French fries with garlic to your cart. What else?
What salads do you offer?
We have market salad, Cobb salad, fruit salad, and side salad. Side salad is popular with our cheeseburger.
I'll do the side salad.
All right. It is sunny out there. Would you like to add some drinks? I recommend our lemonade.
Sure.
I'll have a cola.
We have 2 options: Diet Cola and regular cola. Which one would you like?
I'll take the latter, please.
Adding regular cola. Anything else?
That's it. Thank you.
Okay, your total bill is $24.46. Your food will be available shortly. Thank you.
Thank you.
Thank you. Bye.
Yeah, so as you could have seen, right, there is actually a lot of different, deep learning models which are working in the backend, right from the computer vision side, where we are basically tracking the facial gesture of the person and even their eye movement. Secondly, we are using automatic speech recognition to transcribe whatever the people are saying into natural text. And then we also have an NLP system that is able to have a conversation in a more free flowing dialogue, which is very specific to the food ordering uh, you know problem statement. And then you have text to speech, where the answers generated by the NLP dialogue engine gets converted into this real sounding speech. And then all of that is that speech is then used to further animate the underlying character, which is trying to have a conversation with the humans, right? So again, as you can see, there are computer vision involved, NLP involved, dialogue management involved, text to speech involved, speech to text involved, and doing efficient inferencing across all these workloads on the underlying infrastructure is extremely important. Let me show you another example where we try to do something similar, but in this case, rather than specifically building this uh, system for food ordering, we are trying to attach something like a large language model in order to build like an open domain question answering platform.
Hi.
Hello. Hello, Toy Johnson.
Hi, please ask me anything.
What are the greatest threats of climate change?
The greatest threats of climate change are the effects on human health, food security, water supplies, and the environment.
How do astronomers look for exoplanets?
Most exoplanets are found via the transit method. That was the case for the TRAPPIST-1 planets.
Tell me more about that method.
The transit method is when a planet passes in front of its star. The amount of light blocked tells astronomers the size of the planet. The duration of the transit tells astronomers the orbital period of the planet.
What telescopes use that method?
The Kepler Space Telescope used the transit method to find thousands of exoplanets.
I've heard about a satellite called TESS that is used to find planets. How does it work?
TESS is a space telescope that looks for transits.
What roles do proteins play in our cells?
Proteins are the building blocks of the body. They are the basic materials from which all living things are made. They are needed for the structure, function, and regulation of the body's tissues and organs.
How do they work?
Proteins are made up of amino acids. Amino acids are the basic building blocks of proteins. There are 20 different amino acids that link together in different combinations to form different proteins.
How do they catalyze chemical reactions?
Proteins are biological catalysts. Catalysts are substances that speed up the rate of a chemical reaction without being consumed by the reaction. Enzymes are proteins that catalyze increase the rate of biochemical reactions in the body.
Thank you. Goodbye.
Sure, anytime.
Right, so I think everybody gets the message. That is, going forward, NLP is, I think, one of the most important blocks in the overall um, you know journey of a particular organization, because NLP eventually is going to transform a lot of ways in which the company is trying to build relation with their customers, be it through support chatbots, be it through enabling customers to use their applications and to use natural language to get their task done on the end application. And again, in order to do that, we have multiple examples where chat gpt, which was released a couple of months back, you can see that it's one of the most and the fastest growing application today. The reason why it's extremely fast growing is because this is the first time where people could ask natural language queries and get answers which were, I would say, at least 90 to 95% accurate, and still able to get the answers that they needed. Obviously, there's still a lot of work that has to be done in terms of making these models factually correct, and also ensuring that these models can somehow access the company's proprietary data, and hence building these models, building your own proprietary large language models is becoming extremely important. Now, again, maybe not every organization is going to build 175 billion parametric model, but then there are still a lot of these medium-sized LLMs which are available that are quite easy to serve even today for any kind of organization. So just to give you an example, people these days are trying to build their NLP systems using 11 billion parametric T5 models. They're also trying to use these small size GPT models which have been released in the community like Bloom and others. And that's where there is going to be a major paradigm shift where using these transformer based LLM models are going to become extremely important in most of the business applications. Now, the second thing that is also important is, how do you serve these large language models, or rather say medium-sized language models very effectively? And actually not just language models, but it can be any kind of models. Can be a speech-to-text model, text-to-speech model, computer vision models. How do you actually serve them very effectively? That's another question that people have been asking. And if you look at specifically from the LLM side of things, maybe I'll just take a couple of more minutes to talk about what are the different kind of tasks that we are seeing really good accuracies on, and then I'll move to the side that how can you actually use these different modalities and use efficient serving platforms like Triton, along with a compiler technology which I'll talk about today, which is called as TensorRT and Faster Transformer, to make your inference of these models more efficient. From an LLM standpoint, people are using these models for doing things like text generation, summarization. People are also using it for doing translation tasks. Uh, they're also trying to do code completion, because code completion is kind of text generation, but very specific to generating code. Apart from that, we are also seeing a lot of interest in image generation, specifically from creators like Mid Journey and Stability AI, where you must have seen that people now can provide some kind of text input, and then the model can generate almost realistic human text uh, out of it. So there is a lot of usage of these transformer based models, be it GPT style models, be it BERT style models, be it model architectures like say BART and others. All of them are getting used for solving these different kind of tasks, and they're actually very efficient. So what I really want to do today is I want to set some context of how can you go about taking these models and deploying them efficiently. Obviously, maybe one session might not be enough to show you all the different models at hand, but today I'm going to take two examples. One is going to be of a 11 billion parametric T5 model, and the second is going to be a VIT model, which is basically a transformer model, which is specifically used for doing computer vision tasks. Now, today, if you look at how developers are trying to build the overall life cycle, there are a lot of different challenging problems. But the key problems that we see is, people are not really aware of how do I take these models which are available in open source, say from repositories like Hugging Face, and how do I deploy them efficiently. Obviously, the most straightforward way that people go about deploying these models is to use the underlying framework. So say for example, you will just create a Flask API out of these Hugging Face models, which is running inference on the PyTorch backend. Now again, if you think of it for a quick POC, that's absolutely fine. But is that the best approach towards building large scale inferencing platforms that have to be highly optimized and can give you much better throughput? Probably in those scenarios, the answer might be no. And that's what we are trying to sort of trying to address in this particular webinar. Now, one of the key there are when we look at inferencing or rather deployment as a challenge, there are a lot of different consideration that people have. So what we have tried to do is that I'm trying to give you an overview glance of what are the different kind of uh, challenges could be there in a deployment scenario before we move on to the hands-on part. So if you look at from a deployment standpoint, uh, most of the time these are the six most important problem statements that we hear from people. The first constraint is the ability to do different kind of tasks. So say for example, real time. Now what does real time and streaming basically mean? It basically means that you need to get the response as fast as possible. One of the example for real time slash streaming would be that of speech recognition. Typically whenever we are using a speech recognition system, the transcriptions should be generated in near real time rather than it being saved in some file system and then taking that wave file and running inference on top of it. The former example is more real time because as you are speaking the transcripts will be generated, whereas in the other case you have these audio files sitting on a disk on a file system like a wave file, and then you are running inference on top of that entire wave file. That would be more of a batch workload. Similarly, for a lot of these GPT style models that you use on, say, OpenAI's interface as well, you'll see that the answer that these models generate are token by token, or rather word by word. They do not generate the entire answer. They don't generate the entire answer and then send it back in the UI. But rather, what they do is they start generating the next word again and again over a period of time, so that what really happens is that you get a sense of that application working in real time or in streaming mode. So the underlying inferencing platform should be able to serve these applications either in batch mode or also in streaming slash real time mode. The second constraint that people typically talk about is that, hey, I have models in different frameworks. Sometimes I have it in PyTorch. Some part of my machine learning teams might be giving it through, say, scikit-learn or say XGBoost. If they're just trying to do traditional machine learning, can the inferencing platform also consume models from scikit-learn, like random forest and other algorithms, as well as can it also take deep neural networks like transformers and other architectures from ecosystems like TensorFlow, PyTorch, or Onyx? That's another important question where flexibility is extremely important. The third constraint is that of deployment. That means, can I have this deployment platform served either on cloud or in my own data center or on edge devices or on embedded devices? That's another important and challenging question that the inferencing platform needs to address too. Uh, Next is, how do you serve these models also on different cloud instances? So say for example, if you want to, if your company is using GCP extensively, how do you serve these models efficiently on GCP or even on, say, Amazon SageMaker or on, say, Azure machine learning? uh, right, so the platform that can basically has the flexibility to do all these can be used to deploy on all these different middlewares, that is on any cloud instances, can be deployed either on cloud or on data center or on edge or also on embedded devices, as well as it supports different frameworks and can also support different models, right, from CNN to transformers to RNNs to decision trees and others. And that platform is basically called as Triton Inference Server. So if you look at it, uh, this picture just gives you a very quick outline of how NVIDIA software ecosystem plays a very important role across all parts of the life cycle. But again, we'll keep this conversation very specific to the third and the fourth bucket, which is optimization for inference, which is model optimization, and the second, that is deployment at scale using Triton Inference Server. So let's first try to look at Triton, and then we'll talk about how do we further compile and optimize these models using a compiler runtime like TensorRT. So before I even go ahead and talk about these platforms and show you a hands off of how this is done, I want to probably just take a minute and talk about the and quickly give you an overview of different companies that are using this in real time in production. And again, maybe I don't need to go through all of them. These are like very well known companies that are serving their workloads on top of Triton as of today. And and as you can see, right from Microsoft to Amazon to American Express, all of them are using this, and all of this is public information. You can go ahead and check them out even on our blog posts. Okay, so now maybe let's come back to Triton, and let me give you a little bit background of how the architecture is and what kind of backends does Triton support, and then we'll get into the hands-on part. So if you look at the backends, what kind of backends does Triton support? It is actually a very flexible framework, and it can support all these different backends, right from TensorRT, which is NVIDIA's compiler technology for optimizing neural networks, to Onyx runtime, which is maintained by Microsoft, to TensorFlow and PyTorch. Uh, Additionally, we also support other libraries like OpenVINO, which is built by Intel to run inference on top of CPUs as well. Additionally, if you want to accelerate your data pre-processing, you can also do it using the DALI package that we provide. And then if you're working with machine learning models like say XGBoost, LightGBM, Random Forest, and others, you can also use the fill library from Rapids and serve your models inside Triton. So Triton is extremely flexible. It's not very specifically built for any framework, but it allows you to serve models from all these different backends very efficiently. Now let's look at the exact architecture of how Triton looks like. And this is, I think, an important diagram because it gives you an overview of how the entire life cycle goes across within Triton. So as you can see, on the leftmost side, I have some numbers that you can see, and that is the flow of the entire flow. So what really happens is that there is going to be some front end, could either be in Python or C++, or could also be in Java, can also be in Go. That front end is going to send a request in form of a query. Now again, this query can have input as speech, it can have input as images, it can have input as uh, say mm, text. All those different modalities can be sent through the client. Now once you send this query based on the workload, so let's just take an example of NLP. Okay, say if you're trying to do text classification as a very simple example, the client library will be responsible for sending that query text to the Triton server. Now, what the Triton server will be doing is it will take this query either in form of the HTTP request or a gRPC request. Then it's going to batch the input data. Now, why is batching important? I think this is one question that people do ask a lot. Like, why do you need to do this batching? So, if you look at um, for any large scale deployment, you'll see that you're going to get multiple requests from multiple users concurrently. So say for example, you have built a platform which say in the most simplest form does text classification, and there are say 50 or 100 concurrent users that are sending some input query to your platform. Now one way to do inferencing is you take individual requests from individual users and you put these individual queries inside a scheduler or a queue, and then you run the inference using the backend. Now the issue with this is that you are not really combining these inputs, and because of which you will not be utilizing the GPU to the fullest. If you look at a GPU is majorly built for doing bulk processing. So when I say bulk processing, it basically means that it optimizes for throughput. So the more the load you give, the more efficiency it would have. So say for example, coming back to that 50 queries or 100 queries that are coming in, the dynamic batching system is going to combine multiple requests together and then send it as a single query. So say if you had 50 queries, and if you choose that, okay, the most preferred dynamic batch that I want to create is of batch size 8. So what it will do is, instead of treating 50 queries as single queries, as 50 different queries, it will basically start making batches of 8. So that approximately gives you 6 requests. So rather than processing 50 requests with with a batch size dimension of 1, and dealing with 50 requests, you now only have 6 requests, each with a batch size of 8. So 8 into 6, 48, and then the other 2 queries that will come in will get into another batch. So approximately it becomes 7 batches. So instead of processing 50 requests, it is now going to run inference on 7 requests, where each request will have 8 input queries. Now that makes the overall usage of the GPU more efficient, and that would become very obvious once I show you an example during the hands-on. So in the queue, you get these batched input requests, and then what you're trying to do is you try to run your backend model. Now, if you look at the backend model, you'll see that this model actually comes from this source called as model repository. And what is this model repository? Model repository is nothing but it's a very simple folder structure where you have placed your models. And I'll show you how this looks like exactly when I show you the hands-on. But it's a very simple, folder structure where all these models are placed in different directories. And this folder structure is then ingested within Triton and then served as these backends like TensorRT, Onyx, PyTorch, and so on and so forth. Right. So the input comes in from the scheduler and queue. The models gets the backend gets deployed through this model repository, and then the queue gets processed using these backends, and then you're going to get some resultant output, which you then return back uh, in the same protocol that it came in, either HTTP or gRPC. Additionally, what also the additional thing that Triton also provides is that you can extract metrics of the inference server. That means you can now extract information like GPU utilization, how many requests came in, which model got called how many times. All that metadata information can be queried from the Triton server and can be used for ingesting for doing something like horizontal pod autoscaling. That means you collect all these metrics, you save it in a time series database like Prometheus, and then you can say that, okay, if on a particular GPU, if the utilization crosses 95% and the number of queries are increasing over a period of time, please, automatically scale another backend with all these models and help me load balance all of this together. So all that things can be done by extracting these metrics inside these time series database like Prometheus and orchestrating it through Kubernetes. So again, this is a very high level view of how everything basically works. The next thing that I want to do is also quickly talk about the TensorRT compiler before we do the hands-on. So if you look at the TensorRT as a technology, it's nothing but it's a compiler technology that allows you to take models from different frameworks and optimize it for the underlying GPU architecture. Now, the reason why these kind of optimizations are important is because of multiple different reasons. The first reason is that whenever you call your operators from native frameworks like PyTorch and TensorFlow, you are not really applying any kind of fusion of layers on top of it. Secondly, you are also not optimizing the memory management when it comes to doing inference. So what TensorRT helps you do is a couple of things. First, it allows you to run your model into different precisions, like from floating point 32 to FP16 to even integer 8. Second, it takes the neural network graph, which the neural network model, and optimizes it for the most efficient CUDA kernels that it can find in the underlying library. And this, in return, improves the overall performance of your models on top of the same hardware. So say, for example, previously, if you were getting 1x, Now, by using TensorRT, you will get somewhere between 2x to 3x improvement in performance. Just to give you a quick overview of the workflow of TensorRT, is you typically have a deep neural network model either in PyTorch or TensorFlow. Then you take the ONNX converter, or rather you convert that into the ONNX format. Once the ONNX format conversion is done, then you use the TensorRT compiler to optimize this model and then run this using Triton Inference Server using the TensorRT runtime. There are also ways of running this model inside the framework itself. We also have in-framework integration of with PyTorch and TensorFlow, wherein you just need to change 1 to 2 lines of code, and you'll be able to run the inference in the framework. But the most optimized way of doing things is the top process, which is where you take the model, convert it to ONNX, optimize it using TensorRT, and then deploy it on top of Triton. That's the most efficient way of doing it. So here are very small code snippets for running inference either in PyTorch or in TensorFlow using TensorRT. Here you can see that you simply need to, in case of PyTorch, you simply need to call a new package within Torch, which is torch underscore TensorRT. And then you need to compile that model using torch trt.compile. And then you pass in the model, you pass in the precision, and you give in some input tensor. And this will optimize your model for running inference using TensorRT. But again, these are pretty good to do if you want to do a quick POC. But for production grade workflows, the more recommended path is to convert the model into ONNX, then to TensorRT, and then serving it into Triton. So a quick summary of whatever I mentioned on the TensorRT side, and then we'll go on to the hands-on. So the key takeaway is that the in-framework inference will support any model. There is not a lot of GPU specific optimizations are done, and it also works only in Python deployments. But it has a good ease of use. But if you go with the native way of deploying TensorRT, you will get the maximum performance. Although you will need some expertise of doing the conversion to TensorRT, but I hope in today's session I'll give you a general outline of how this is done, and it should help you to do the conversion much more smoothly. Okay, so let me quickly stop my slides and get back to the hands-on part. So the first example that I'm going to show you is that of the vision transformer. Okay, so this is nothing but it's a transformer model used for vision tasks. Just to give you an example, you can just go into PyTorch vision VIT. So this is the model architecture that we'll be optimizing for, called as Vision Transformer. You can read more about this model architecture in this paper as well. And we'll be taking one of the models, which is VIT_B_16 over here as a pre-trained model. Okay, so let's get started. So what I'm doing here is pretty straightforward and simple. I import the torch dependencies, which is torch.nn and torch vision.models. The second thing that I'm doing is I already have a custom VIT model over here. This is the path to that custom model that I have used. And then we will be taking this PyTorch model and we'll be converting it into the ONNX format. That is the step one. The second thing that we'll be doing is we'll be converting this model also in the TensorRT format, and we'll save it in this folder called as TRT32. And we are also going to convert this into FP16 and save it over here. So these are just the paths of where the files will be saved. The next thing that I'm doing is I am calling the VIT model architecture over here, and I'm adding some additional feed forward layers on top of this model over here. So we take this model, we add an additional classification head on top of this, which is nothing but nn.linear, and then we are going to export this model into Onyx. So in order to export the model to Onyx, there are very simple ways of doing it. Just a second. Yeah. So what you really need to do is you need to call torch.random. This basically means random number. Then you need to pass in the input tensor size. So in this case, say my batch size, I've taken it as 8. This is the batch size that I'm passing. And the input shape is going to be 2 to 4, comma 2 to 4, comma 3. The reason why it's given in channels height width format is because typically PyTorch expects channel height and width as the input format. If you're working with TensorFlow, it might be something like height, width, channel. Okay, if you're working with TensorFlow. Okay, so what we do is we create a simple tensor of this particular shape. So here, if I just do example.shape, you can see that it's a batch size of 8, 3 channels, height is 2 to 4, and the width is 2 to 4. The data type is float 32, and the device is on CUDA 0 device. And this is the input tensor. Now the next thing that I need to do is I need to take this input random tensor, and then I need to pass it to my underlying model. Now here, instead of 8, I've just replaced it with a batch size of 1 as an example. And I'm doing torch.onyx.export. I'm passing in the model. I'm passing in my input tensor x, and I'm also passing the path where I want to save this Onyx model. Then we also provide some additional parameters like export params and offset. For now, you can just safely ignore these two parameters. You can also work with the default offset values. And then this is an important part, which is what is the input and output names and the dynamic axes. So input name is nothing but the name of your input layer. So this is going to be the input layer name, the first layer, which will be called as input, and the output layer name, which is output. Now the other thing that is also important is the fact that you want to keep your axes variable. Reason why you want to keep it variable is because you might want to run inference with different batch sizes, and not maybe specific to one batch size. So that's where you need to provide dynamic axes input, and then 0, and then just batch size. This will export the Onyx graph with dynamic axes. So yeah, so you do things till here, and the output of that is going to be, you can just go inside models. You can see that this is the model that will get saved, model.onyx. So yeah, so this step will get you this particular model called as model.onyx. Now the next step is the TensorRT conversion. Now what I'm going to do today is I'm going to share the most simplest way of doing this conversion. Obviously there are different ways in which you can do it. You can use the Python API, you can use the C++ API, or you can use this CLI command called as trtexec. So what trtexec does is that it takes your input Onyx model, which is the same model.onyx that you saw, take that as input, and for now just look at these 4 parameters. So OPT shape. So what does OPT shape basically mean? OPT shape means that I want to optimize it for the batch size of 8. That means in my production environment, I think that a batch size of 8 is going to be very common, and I want to optimize this model for a batch size of 8. Now again, this is just one of the optimization shape that I'm giving, but you can set what is going to be the minimum shape and what is going to be the maximum shape. That means your TensorRT model that gets created through this process will not be able to take a model with a batch size greater than 128, and the smallest batch size that it can take is 1, and it is optimizing the engine for a batch size of 8. This is what it means, and that's where you see that OPT basically stands for optimization shape. maximum shape stands for the maximum input tensor that the model can take, and the min shape stands for the smallest tensor that the model can take. So just to quickly tell you, this model can take input right from 2 comma 3 comma 224 comma 224 till 128 comma 3 comma 3 comma 2 4 comma. Any tensor which does not match with this dimension will not work uh, with this TensorRT engine. So please be careful and decide these parameters based on your production requirement. I'll give you some more pointers as to how do you roughly and mentally think about choosing the maximum shape, right? So think about your use case in terms of what is the underlying hardware that you're using. So say for example, if you have limited amount of GPU memory, say if you have 16 GB of GPU memory, you can keep a max shape a little smaller so that when you send a large batch size, it does not go out of memory. So what you'll have to experimenting and tweak out is you'll have to find out what is the best shape that can fit efficiently on top of that GPU card that you're using. And based on that, you choose the maximum shape. Now, when it comes to the minimum shape, this is typically a no-brainer. The best way to think about it is that you always choose the batch size as one, right? Because this is the smallest input request that can come in. And OPT shape is something that you can decide that what is the typical pattern of your requests that are coming in, and you can basically choose and tweak around this parameter as well. So you can try out different optimization shapes and see which works best for your underlying model. So this will basically run the TensorRT model conversion. I've already done this because this takes quite some time. You can see that a lot of metadata information will be shared over here of the conversion process. I've already done the conversion, so I will not mm, do this again. But this is how the conversion process happens. But I just want to show you some important characteristics of what happens when you do this conversion. So let's give it a couple of seconds. What will happen is that you'll see some GPU utilization when you're trying to do this conversion. The reason why this happens is because the TensorRT compiler is trying to find the most optimized CUDA kernels for these shapes and for your model. So what it really does is that it's trying to run different kernels and it's trying to find the best kernels. It's trying to fuse different layers together so that you get an optimized engine. And that's where you'll see that there is some GPU utilization that will start happening because it's trying to do all those processes in the backend. So this will keep going on. This takes quite some time. There are a couple of more optimization things that you can try out, which is things like CUDA graph. Like you can just pass in a parameter called as uh, minus minus CUDA graph. You can also enable this particular parameter as well. But again, just for today's session, I'm going to keep it extremely simple with uh, the most basic parameters that you need for today to get started. So this optimization process takes quite some time, like about 4-5 minutes to build this engine file. And yeah, so I'm just going to stop this for now as in interest of time. Additionally, you can also convert this to FP16 by passing minus minus FP16 as a flag. So this is FP32. When you do this with this flag called as minus minus FP16, this will run with floating point 16. And if you pass this with int 8, it will run it in int 8 precision as well. So these are the different precisions that you can use. Typically, FP16 is the most safest option because you will not undergo any overflow or underflow problems in your forward pass. Int 8 sometimes requires some additional thought in terms of doing this optimization because integer 8 has a much smaller range uh, overall compared to FP16. So there is a chance that you might see some loss in accuracy, but There are some really good tricks like uh, post-training quantization and quantized aware training that can help you to mitigate those accuracy errors and still run your model efficiently on integer rate. But FP16 is the safest option, and this is what is most recommended. For integer rate, you might have to do some more experiments and find out. Okay, so I have already done this, so I'm not going to repeat this part. I'll just show you the models that get generated from this entire process. So just give me a minute's time. Okay, so let's look at the TRT FP32 model. The model size is about 669 megabytes. And as you can see here, the model size actually shrank to almost half. The reason why it shrank to half is because you went from floating point 32 to floating point 16. That means you have reduced the size of the model by half. Additionally, when I'll do some performance benchmarks, you'll also see that we have also improved the performance again, it depends on the model architecture. Sometimes you might get 1.5x, sometimes you might get 2x, 3x. It all depends on the model architecture. So yeah, the size of the model has reduced by half over here. Now let me now these models will be ready. After these models are ready, the next thing that you need to do is you need to create your Triton model repository. How do you build your Triton model repository? If you remember, while I was showing you that slide, you must have noticed that in the Triton model repository, uh, I mentioned that it's a very simple folder structure. So let me just install tree. Sorry, it's and just show you how the folder structure looks like. And again, it's extremely easy, very um, easy to install tree. Okay. So in this particular folder structure, you can see that this is the name of my model. And within this, I have two files. The first is called as config.pbtext, and the second is a folder called as one. And then there is this model.plan file over here. The same thing also for the VIT TRT FP32. So let me maybe describe this in a little more detail of what these files basically mean. So the config.pbtext is nothing but it's a configuration file. This configuration file needs to have information right from the name of the folder. What platform is it using? I'll come to dynamic batching in a bit. Maximum batch size. So again, if you remember, while we were trying to do the TensorRT conversion, the maximum batch size that we chose here was 128. So you'll have to mention this particular value in your max shapes over here. The second thing is the input. So which is your input node. So if you remember, while we did the ONX conversion, my input name was input and my output names was output. Now this is considering that your model takes a single only has a single input and a single output node. There can be situations where you might have multiple input node names, multiple inputs, or there can also be a situation where you might have multiple outputs. So all you need to do is you need to just additionally pass those names also over here, right? Like say input one, input two, output one, output two, and so on and so forth. So yeah, so here you can see that this is my input dictionary. Here my node name is only input because there's a single input. The input data type that I need to take is FP32. The dimension is going to be 3,224,224. This is the shape of the input image. And then I'm going to get an output. Now, what is my output? Output is nothing but a probability for 4 classes. So this custom VIT model that I've used for doing optimization was fine-tuned on 4 classes, 4 different classes. So you have your dimension mentioned as 4 over here. If you take a pre-trained model from ImageNet, this dimension will turn out to be 1000. Okay, so again, the dimension would change based on the number of classes that you have, in your trained model. The next thing is the instance group. What is instance group? It is nothing but you can also host multiple instances of the same model. So, so think of it like this: you have one instance of this model running, But say based on your load, you want to deploy multiple instances also. So say for example, you want to run 2 instances of this model, 3 instances, you can also do that as well. So the way to do that is you just increase the count over here. So change it from 1 to 4, say 1 to 5, 1 to 8. Please note one thing, that always increasing the instance count will not always give you performance improvement. This is something that you'll have to experiment and test out with, like what is the optimal instance count that you need for your load. So this is a hyperparameter that you will have to tweak around. Second parameter is kind GPU. That means you run it on this on GPUs. If you move it from kind GPU to CPU, the TensorRT engine might not work, but the PyTorch, TensorFlow, other models, and OpenVINO models will work. In that case, you'll have to set this as kind CPU. And because this is kind GPU, you can also mention if there are multiple GPUs in your system, you can also mention on which GPU ID do you want to place this model on. So this is the entire very simple configuration file over here. And again, if you look at the other model also, it will also have a very similar configuration file. Okay, so one last thing that I want to also highlight is this folder one. What is this folder one? This folder one basically means this is the versioning of the model. So there can be situations where for this model, you might have multiple versions like version 1, version 2, version 3. We also provide a flexibility of hosting multiple versions of that same model as well. So you can say 1, you can say 2, and then put your models inside of that. And then you can also put the model version over here as to which one do you want to use for production. So I hope at least it gives you an overview of how the structure looks like. Obviously, there are a lot more details that we'll cover in the upcoming sessions, but just wanted to quickly show you how this folder structure looks like. Now, what I'm going to do is I'm going to quickly run some performance benchmarks. Okay, so let's quickly do that. Um, just give me a second. Okay, so I think it's on the tab. Okay, so I'm running 3 different kind of loads, and maybe I'll just do watch NVIDIA SMI. I think it's not going to run here. Um, just give me a second. Let me open my terminal. Let me share my terminal. Just a second. Okay. Oh, could somebody confirm if my terminal is visible? Can you see a white terminal that shows some GPU utilization? Okay, great. So as you can see, right, that perf benchmark, that perf analysis command that I ran is basically responsible for creating artificial load and then sending that artificial load on top of the GPU to stress test and to find out what is the throughput and latency that we can expect in different scenarios. So here, the first run was done. I'll do the second one and then I'll show you the results as well. Just give me a minute. Okay, so let me run the first one. And now here you'll see that the utilization is very low, right? It's somewhere around, say, sometimes it goes to 466, right? Comparatively, the utilization is quite low. Now, why is it low? This is low because I'm trying to just hit the FP32 model with only one concurrent user. That means there is only one user who is sending request to this model. Now, in order to increase this, what do I need to do? I would want to have multiple simultaneous users sending their input requests. So now I will run it with the same FP32 model, but now with say 4 users. Now you can see that the GPU utilization did increase to approximately 91, 92. Okay. This basically means that now I have more users sending input request to my model. Okay, this is also done. And now I'll run the final one, which is my FP16 model. And here I will further increase the overall load. So yeah, now let me go back to the results and show you, how does the model perform over different load scenarios, and how does it differ from FP32 to FP16. So I'm going to move back to my benchmarking window. Yeah. So here you can see that, when I was only sending a request of one, you can see that my overall throughput was very bad. It was just 61 images per second. But now when I increase the concurrency to 4, that means I got 4 simultaneous users hitting this particular server. You can see that my overall throughput increased to 613 images per second. This is almost like a 10x jump. Now, if I then further use the FP16 model and also double out the load, you can see that I get approximately 1234 images per second. That's another improvement by almost a throughput of 2x. So again, the whole point of this was to give everyone an overview of, how you can use Triton inference server to deploy these models, how you can use TensorRT to compile and optimize these models for lower precisions, and how you can use these perf analyzer tool to do performance benchmarking on top of the server, and to roughly estimate how much throughput and latency your models are basically giving with different load scenarios over here. I want to show you one last example of T5 model and show you how much improvement do we get compared to the Hugging Face deployment. So I've also deployed a T5 model in parallel. So here I'm using a T5 11 billion parameter. Sorry, here I'm using a T5 11 billion parametric model, and this model is called as FLAN T5 XXL. This is the model that I'm using. And now I'm going to run inference using the Hugging Face interface, right? And then let me just do God. Yeah, let's run this and then also run this. Let me share my terminal window where this inference will be going on. Just give me a second. Yeah. So as you can see, this is where the performance analysis is happening, right? There's a lot of utilization, and it has basically now stopped because the inference is basically complete. Maybe let me just rerun it so that just a second. Let me rerun this. Yeah. So here you can see that first I'm running it for Hugging Face. It's running it for the Hugging Face interface. And now we are running with the optimized version of this using Triton. And just a second, let me show you the performance benchmark numbers. And again, the best thing is all of these SDKs are all open source. That means you can go ahead today and run this for your workloads in production and run them using these open source tools. So here you can see that the Hugging Face interface for this particular question for 11 billion T5 model gives me a latency of 395 milliseconds. Okay. And the same thing when I run it with Triton along with the faster transformer, or say even TensorRT for that matter of fact, I'm getting somewhere around 83.3 milliseconds as my latency for running this. So if I just basically divide these two numbers, which is 429 divided by 83, you'll see that I get approximately 5x reduction in the overall latency. So this is again a very important thing. That means, on that same underlying hardware, just by using these right SDKs, you can get somewhere between 2x to 5x improvement for your model deployment. And again, all using open source tools. So in the interest of time, I think this is where I would conclude. Obviously, there's a lot of more details that would be there in terms of, how do you combine multiple models together? How do you combine pre-processing, post-processing together, along with this optimized model version and all of that. So what I'll do is in the next couple of minutes, I'll just take in all the questions from the chat and QA. Just give me a minute. Okay, so The first question that I'm seeing is how can I start using open source version of Triton? Can you send a blog post documentation where I can get step-by-step link? Yes, let me quickly do that. Just give me a minute. I'll share that link over chat. Okay, so I've shared the link of Triton. I'll also share the link of TensorRT. There are multiple code blocks which are also given over there. You can also look at those code blocks as well as a reference. Let me go to the next question. Is there a place where we can monitor the GPU metrics in one place? Any plug and play frameworks available? So you can look at GPU metrics through, I mean, if you're trying to serve it in an inference server, then you can obviously extract the metrics from Triton itself. There are easy Python APIs that can be used for doing that, and all that information you will find it in the Triton inference server GitHub repository. There's another question uh, I have a project which involves almost 5 deep learning models for processing of a query. Which platform do you think is better and efficient to deploy and host as a dynamic website that can serve it in a robust way? So the best way to do this is actually to use TensorRT along with Triton. And again, there are multiple different frameworks. Obviously, you can explore those out as well. But within Triton, we also have this concept of ensembling multiple models. That means if you have 5 different models that run together, you can chain all these models together simply using the Triton ensemble, and that would be extremely efficient. So yeah, my recommendation would be to try out Triton Ensemble. Maybe we'll have a specific webinar where we'll try to cover different kind of ensembles and how to build ensemble Triton instances. There's another question for large-scale inference workloads involving models developed from both deep learning frameworks and ML algorithms, uh, which don't use GPU. Can you make use of Triton architecture? Yeah, the answer to that question is yes. You can absolutely use Triton to also deploy it on top of CPUs. The advantages of GPU is that you would get better, better performance for your money. But again, I would leave that up to you to explore and figure that thing out. But yes, you can make use of Triton even if you're not using GPUs. You can also run Triton on top of CPU, so that's fine. Another question is, what is minimum required hardware to use TensorRT efficiently? Is there any free access platform for research in AI using GPU resources? So TensorRT supports almost all latest GPU architectures, right from uh, the Pascal series to the Volta series, which is the V100s, T4s. Apart from T4s, you can also get RTXs. It will run on almost all GPU architectures. But ideally, you should be looking at anything above Volta, because that is where we introduce the tensor cores for FP16 inference improvement. There's another question: is the conversion to be done before training the model? No, the conversion happens only after training the model. So TensorRT and Triton comes after you have trained your model and now you're looking at deploying it. Another question is, explain the main problem that TRT is used to solve. So TRT is used to optimize your neural network model architecture for the underlying GPUs. So it will do things like it will fuse a lot of these deep learning operators together. Like, just to give you an example, say you have convolution, batch norm, and ReLU. These are 3 operators that are there. So TensorRT will basically, instead of calling these layers individually, the compiler will fuse these together as one single operator. So that will basically make the number of operators less, and then you basically do less number of CUDA kernel calls. So it's a very efficient way to optimize your model and to get better performance. So if you're running your models in PyTorch or TensorFlow, it's always recommended to use TensorRT, because that will improve your overall performance on that same GPU architecture. There's another question: how to give multiple input and output in config.pb text. You will find that information inside the Triton GitHub repository. So it's I'll share that information over chat, but I think there will be a session specifically for where we'll talk about model ensembles, where we'll show you how to have multiple input and output in config.pptext. But in short, you should be able to find that information in the Triton server GitHub page. So yeah, I think yeah, I think I've addressed most of the questions. Uh, okay, I think most of these questions are answered. Yeah, thank you so much everyone for joining in, and we'll share all the links again, maybe over the mail in our communication channel. Thanks everyone.